All right, here's the calculation for a t-test, right? Numerator is the difference between means of group 1 and group 2. Denominator is the difference within group, right? Variability within group. The standard error of the difference between group means, standardizing the mean difference for between groups. So when we adjust for between over within, we're saying how many within steps does it take for us to actualize the difference between groups, right? Much like a standard deviation would. Standard deviation within a sample just says how many standard deviation steps does it take for us to get to the next group. T-test, a bunch of different t-tests. The t-test compares two group means to see if there's a difference. So it's exactly what we've been doing this whole time. There are three kinds of t-tests. One t-test that compares a group mean to a population mean. One that compares a group mean to that same group's mean at a later point in time, right? So still we're comparing means. And then the bolded one here, the one that compares one group mean to another group's mean. So broken down, these are called the one sample t-test, the one that compares my mean of my sample to the mean of the population to see how different they are. Oftentimes, you don't have population information. Now, if you sampled from the population a representative sample, and you also have data for the population, you can compare. The problem is oftentimes you don't have population parameters. That's the whole reason you're taking the sample is because you don't have population parameters, right? So you don't see this that often, right? Where people are comparing one sample to the population. You do, however, see paired samples t-tests or repeated samples t-tests, right? You want to compare the mean at time 1 to the mean of time 2. So here you can only compare 2 time points. And then finally, what we've been doing this whole time, independent samples t-test, right? We're looking at 2 samples, looking at the mean of them and comparing them. As you know from your bivariate relationships check, the independent variable for a t-test is nominal or ordinal. It's a categorical or grouping variable, right? And those groups are comprised of only 2 attributes, right? Black versus white, middle class versus working class, right? You can only have 2 groups that you're comparing. Right? And then our dependent variable is interval ratio or continuous, as some say, right? So we're looking at means and mean differences as the outcome. If you're looking at means, you have to have an interval ratio variable. Independent samples t-test, the null hypothesis is that there's no mean difference, right? Just like the z-test we've been doing, no mean difference between these 2 groups, or the mean of the dependent variable does not vary by group, right? So that means that the mean of group 1 and the mean of group 2 in the population should be expected to be equal. Right? The alternative hypothesis is that the mean difference between these 2 groups does exist, right? They do vary by group. So mean of group 1 in the population does not equal the mean of group 2 in the population. There is a difference. The null blames everything on sampling error or chance, says any difference you do find doesn't represent a true population difference, while the alternative says any different or tries to explain away difference not as sampling error, but as true population differences, right? So we have the 2 poles, right? The alternative hypotheses and the 2 poles, and then the extreme version of the null hypothesis in the center. So if we end up with a t-score, a t-value that's in the tails of the distribution, then we've crossed that finish line, we reject the null hypothesis. So these are assumptions that can't be violated when you're running a t-test, independence of observations. So what this means is that these groups cannot be dependent on or related to one another. Right? You don't want to take a sample of 2 groups and then in one group you have husbands and another wives or partners. This is because, especially if you're looking at like marital outcomes, those answers might be related to one another. So that's going to bias your results between looking at true null and true alternative. One way that people get around this is representative sampling, random assignment to groups, and then you test these differences. Oftentimes in social research, we can't randomly assign people to groups because the groups we're interested in already exist. You can't assign someone to black or white or smoker or not, so on and so forth. The way we deal with that is randomly sampling. There are ways to deal with if you don't random sample. Right? You can run permutation tests of your t-test by shuffling the grouping value. Can you get similar results? You want to ensure that you have equal sample sizes or equal group sizes, because variability within each group is a key component of the calculation. If you don't have enough variability within each group, how is the calculation going to work? With one case, variability does not exist. If you have one case, you can calculate the mean. It is just that person's value. Variability is non-existent. It is NA. If you have two cases, there's variability, right? With increasing numbers of cases, you're going to have more variability. Not saying that the variance or standard deviation will grow, but you're adding variability to the calculation. So while we say here equal sample sizes, equal group sizes is important, what's important is increasing the sample size. So you want a representative sample, a random sample, but you also want large groups. You don't want to be doing t-tests on group 1 has 5 people, group 2 has 5 people, right? You want to increase sample size. If you do violate it, you can use the pooled variance t-test formula. I don't think I've ever used the pooled t-test formula except for while running it for an undergrad stats class once. The issue that you'll run into is dealing with the variance calculation, right? The variance within group calculation. So how do you deal with that? With this unequal variances assumed option. Homogeneity of variance basically just says that you have similar kinds of variance within each group. Because you're comparing variances, if you have unequal sample sizes or not enough people, you can have wildly different variances, which is going to contribute to the overall t statistic. How are we supposed to adequately compare these two groups if they're not essentially similar? The idea here is that you want to see that both groups have approximately the same variance, and variance is just standard deviation squared. So if you're looking at variance statistics, you want to see that there's a 10-to-1 ratio and nothing more, right? So one group's variance cannot be more than 10 times the amount of the other group. That's a wide range of variance. When you're looking at standard deviations, you can say about a 3-to-1 ratio. You don't want the standard deviation for one group to be over 3 times the amount of the other group. You're controlling for everything by those variances, so you want them to be about the same. You don't want one to have larger effect on controlling the difference between these groups, which contribute to the shrinking of the t statistic. And then normality of distribution. Luckily, we've done the normality stuff before. You can look at a descriptive statistics table, or you can just visually inspect. Look at the histogram, does it look normal? QQ plots, do they look normal? Do all the dots follow the line, or is there a pattern that we don't want to see? And then box and whiskers plots. Do we have any outliers? Is the median right in the center? If you violate this, you can use this option of unequal variances assumed, but often we're going to assume equal variances. I said it alters the t-distribution when you estimate a parameter from statistics. So what we have to do is adjust our curves. Curves are going to be different based on the sample size. And it's not just sample size, it's what we call degrees of freedom. Degrees of freedom, one way of looking at it is we have to estimate some parameter in the population, but we're relying on data from our sample. Our best guess of the mean in the population is whatever we get from our sample. And if we think about it, if you have to calculate the mean, you can have up to n-1 of those values vary. So what I mean by that is if somebody told you the mean age in this class is 23, they didn't tell you any of those numbers, what you could glean from that is, okay, I know that, let's say there are 30 people in the class, the mean age is 23. 29 of those cases could be any value in the world. But if you have 29 of those cases, there's only one possible value left to make it a mean of 23. You have one possible value left. That value is fixed. And that's the logic that goes into degrees of freedom. If we look at the curves on the right, we're estimating curves based on sample size. The x-axis down here, we see the solid line is the normal curve with df equals infinity. All the way to the right, we have the dotted line, indicating a df, degrees of freedom, of 1. We can think of degrees of freedom as just sample size minus 1, right? Sample size minus 1, sample size minus 1. We're adjusting for sample size. We're adjusting these curves for sample size, knowing that we don't have the population parameters, knowing that we don't have a large enough sample that would represent everything that's in the population. You see here that the calculation down here for degrees of freedom is n1, the number of cases in group 1, plus the number of cases in group 2 minus 2. So if we broke this out, it's basically just n-1 plus n-1. So if you have 100 cases, 50 in group 1, 50 in group 2, so 50 plus 50 is 100 minus 2 is 98. You have 1,000 cases, 1,000 minus 2 is 998. Degrees of freedom is basically an estimate of sample size. So as sample size goes up, so too does degrees of freedom. So what we see on this right-hand side is as sample size goes up, the curve, the t distribution becomes less and less platykurtic, all the way up to infinity degrees of freedom. So if you have infinity cases, you're going to have a normal curve. But as you decrease sample size, the distribution becomes more and more platykurtic. So it's adjusted for by sample size. So recall that we did this. If the z calculated is greater than z critical, then the difference is large enough to be counted as extreme. We can't blame it on sampling error. That means our z is going to be in the rejection region, therefore we reject. Therefore p is less than alpha, therefore we have a statistically significant difference. Now, we replace z with t, and that same logic holds. If our t calculated is greater than our t critical, then we're in the extreme region. We cross that finish line. We are in the rejection region. We reject the null. P is less than alpha, statistically significant difference. I switched this up here because sometimes we refer to calculated as obtained, right? The t obtained versus the t critical, or the t calculated versus the t critical. Also recall that if we had an alpha of 0.05, our critical value for z is 1.96, right? Now we're working with not one probability distribution where those rules apply, right? We know everything that happens with the normal curve. We're dealing with a bunch of different curves that happen to be more platykurtic as sample size goes down and less as sample size goes up to and possibly equal to a normal curve. So what that means is we have to adjust our t critical value based on whatever curve we're dealing with, whatever sample size we have. We can't just rely on 1.96. Because it has multiple distributions based on degrees of freedom and an alpha level, we have to figure out what the cutoff is. It's not always going to be 1.96. If your alternative hypothesis is directional or non-directional, I said we're always going to be using non-directional, right? Possibility that you can switch the groups and get negative or positive values. You figure out what your alpha level is, your degrees of freedom, so number of cases -2, and then you evaluate to see if your t obtained is greater than or equal to your t critical that is found in this table. So I'm actually going to open that up. So instead of having one set of rules, we have a bunch of different rules for different levels. We figure out if our hypothesis is non-directional or directional. We're going with two-tailed tests, so it's non-directional. Our alpha level, if I don't specify an alpha level, we know that our alpha is going to be 0.05, and then we figure out degrees of freedom. In our example, we had 30 people who identified as liberal, 30 who identified as conservative. Knowing that we have 30 and 30, that's 60 people that we're looking at. So for us, our degrees of freedom would be 30 minus 1 plus 30 minus 1, or 60 minus 2, 58. So our degrees of freedom is going to be 58. So we have an alpha of 0.05, degrees of freedom of 58. And we can use that to figure out what our t critical value is. Here we have level of significance for a one-tailed test. Are we using one-tailed? No, we're looking at both tails. So we're using a level of significance for a two-tailed test. Although it says significance here, what it's talking about is our alpha level. So this is going to be our alpha level. Our alpha is going to be 0.05. So is 0.05 equal to 0.5? No. Or 0.4 or 0.3 or 0.2? No. 0.1? No. 0.05. There we go. So we're going to be dealing with this column right here. This 1, 2, 3, 4, 5, 6th column. Well, if you want to count degrees of freedom, 7. So this column. Then we figure out what our degrees of freedom are, and where those two lines intersect, that's going to tell us our critical t value. All right, so we have 58. So it goes all the way up to 30, and then 40, 50, 100, and infinity. So let's try 50. Let's just look at 50 because it's between 50 and 100. Let's try 50. So 0.05 down to 50 here. Our critical t value is going to be 2.009. You might say, because you had over 50, why didn't you go further down? Why don't you just go to the next level up? Well, let's think about it. Here at 50, our critical value, the finish line, is at 2.009. If you go down 1, our finish line becomes 1.984. What we want to do is be stringent enough. And if you're stuck between two values, you want to take the more stringent of those values. So if I'm choosing between 1.984 and 2.09, I want to pick 2.009 because that's further away. We want to be stringent enough that we're not committing what we call a type 1 error, right? Saying that something is a significant difference when it's truly not. However, unless you're an undergrad taking an undergrad stats class where you're actually writing this stuff out, you're not going to be using this table. This table is provided for when you have to select the T critical value. Luckily, we have programs to do this. Programs have T tables built into the analysis. So it will find the exact T value based on your exact degrees of freedom, and it will calculate that for you. You'll notice as you go up this degrees of freedom list, you're getting fewer and fewer cases, right? Degrees of freedom is basically equal to sample size. So this would be 102 cases, this would be 52 cases, this would be 42 cases, so on and so forth. So if we had degrees of freedom of 1, our cutoff value at 0.05 would be, 12.7. But just earlier, when we had 58 degrees of freedom, our cutoff was 2. How did it jump from 2 to 12? Well, part of that is the amount of variability that exists in the data set. If there's not enough variability, how can you say that this difference is representative of what's going on in the population? You're less and less sure with fewer and fewer cases. With 3 cases, you have to be so far off the charts with a z-score or t-value of 13 before you can say, okay, this is a true difference. But you violate some of the other assumptions as well. So basically, don't do this. You'll also notice as you increase sample size, these numbers start going down and down and down and down and down, all the way to infinity, which is a cutoff of 1.96. And we said, as you approach infinity, as you approach a lot of cases, you're getting closer and closer to that normal curve. So what this means for us is that we often, with a lot of cases, we're still striving for this 1.96. But if you have fewer than 100 cases, you're going to be looking for something more stringent. So with our 2 groups that we compared, with a value of 2.0 and a critical value of 2.009, do we reject the null hypothesis? So we're comparing our calculated value. Let's assume that that's now a t value of 2.0. So our t obtained is going to be 2.0. Our t critical is going to be 2.009. We have not yet crossed the finish line, right? So given that we haven't crossed the finish line, are we in the rejection region? No, we're outside the rejection region. So if we're not there, then we fail to reject the null hypothesis. We fail to reject when we're on the other side, when we don't finish the race. So we fail to reject the null hypothesis. Do we have a statistically significant difference? No. If we reject the null, that means we have a statistically significant difference. If we don't reject the null, we don't have a statistically significant difference. So P is going to be greater than alpha. So then we evaluate to see if T obtained is larger than T critical. And we saw with that example that T obtained is not larger than T critical. Reporting T, when you report T, so writing it up, the test you use, so t-test, independent samples t-test, if you reject or fail to reject the null hypothesis, the variables used in the analysis, and T, the degrees of freedom, calculated value of the test, so the obtained T value as well as the P value. So we say T of a certain number of degrees of freedom equals whatever our T obtained value is. The P value is equal to or greater than or equal to this value. And then to write it up, you say using an independent samples t-test, I reject or fail to reject the null hypothesis that there is no difference between group 1's mean and group 2's mean. Or you can say there's no mean difference between group 1 and group 2 in the population. T of a certain amount of degrees of freedom equals whatever the T obtained value is. P is either greater than 0.05 or less than or equal to 0.05. And then I have this example here that we can walk through, but I won't do that now. I do want to point out that you can use the confidence interval formula to calculate a confidence interval around the mean difference. So you can say mean difference plus or minus whatever your T critical value is, and then your standard error of the mean. So on the course website, we have R resources, and the R resources is a link, I think, to getting started with R. you can get to all of the stuff we're going to be doing in this class via this vignette. So each page has a set of vignettes. So anytime we're walking through something in class, we're going to be walking through using that. When I say we're working with R, I'm assuming you have the vignette open next to it, right? And that's because every time we have code, it's going to be separated by this gray bar, and you just highlight and copy and paste into R. Also, you'll see that when you click on, let's say, univariate stats in normality, next to it will pop up an R script. I don't know. Yeah, this one should work now. Right. It doesn't allow me to have it download for you, but you can just highlight everything, copy and paste it into your R window. Let me pull up this R window. I'm actually going to shrink this a little bit, move this over. You can copy and paste it, and it's going to be all of the code that you need for running everything for this assignment. So this is everything from the univariate page, basically just pulled out, right? Here, it's all of that stuff, but with description and written out, but here's just the R script. When you turn in your assignment, this is what I mean that I want you to turn in everything from this R script window, right? You highlight this, you copy and paste it to the last page of your assignment for the portfolio, right? And this means like start a new page, say R script at the top, and then copy and paste it into that page. Do not copy and paste in line with the assignment. But this is what I mean when I say copy and paste the script window, not the console window, because the console window will have answers in it. And that's not what I want to see. Because this is the replicable part of it. Like if somebody wanted to rerun the assignment that I did, they could just copy paste this and rerun everything, and it should give them the same results as mine had, right? That's what that's for. So I will go back, go to t-test. You'll notice that it just says t-test example here, but when we open up the t-test, it'll say t-test example, but also R script, and we can open that up, and there's the R script for you, and you do the same thing. So let's scroll through. So what's the t-test? The t-test examines differences between two groups, the differences in means between two groups, in an effort to see if the differences reflect true differences that we would expect to find in the population. So I'm going to actually just copy and paste all of the R script into my window here. Go back. So I have loading the libraries, right? Loading the packages. I have those here listed in my window. I made an update to the VanStats package, but because it's not on the R network on CRAN and it's on GitHub, I've had to install it this way or reinstall a newer version of it. So in here, I have that listed there. So I'm just going to highlight all of those, run. Cool. For all of you, I know we've had some problems with downloading the R VanStats package. So if you don't want to run that line of code, you can just put a hashtag in front of it. It'll green it out, and then it'll just load the version you already have. All right. So assumptions and diagnostics for the t-test, right? So the assumptions for the t-test, as we can be reminded, is that we have independence of observations, equal sample sizes, homogeneity of variance, and normality. Right? So we're going to be using the mtcars data set. We're going to create an object out of the mtcars data set, call it data1. So instead of calling, I'll actually remove this. I'm going to load mtcars as data1. Independence of observation. So how do we know if these things are independent of one another? How do we know we met that assumption of independence of observations? Well, we have to examine what's going on with the data collection strategy, right? What we are looking for is that cases are not dependent upon one another, or people in one group aren't related to or dependent upon people in another group. Here with the MT-CARS data set, we're not looking at people, we're looking at cars, right? So depending on how we're slicing the data, what our groups are going to be, then we can figure out, are the groups related to one another in any way? But just for the sake of this example, we'll say that these were randomly selected data of cars. I think it was in 1979. So MPGs and everything for cars aren't going to be dependent upon one another, right? Some automakers make gas guzzlers and they also make fuel efficient cars, right? So we're not going to say that they're related to one another in that way. So let's, at face value, let's say we can assume that there's independence of observation, right? Equal sample sizes, right? We have to examine the N for each group, the number of cases for each group. They should be relatively similar. Homogeneity of variance, right? So we want to examine the standard deviations, and we want to see that the variance is 10 to 1, but the standard deviation, since that's what we're calling, will have a ratio of 3 to 1, right? Or no more than 3 to 1. So with equal sample sizes and homogeneity of variance, those two, so assumption 2 and assumption 3, we've already met number 1. For assumption 2 and assumption 3, we want to use that describe by function. So we can use the describe function. It's going to give us all the descriptive statistics for all of the data. But since we're interested in a relationship between two variables, we're interested in how the mean of group 1 differs from the mean of group 2, then we have to break out by those variables. Here, I'm interested in understanding how MPG varies. So mean MPG varies by whether or not it is an automatic transmission car. Is it automatic or is it manual, right? Manual cars are number 1, automatics are 0. So we calculate this, describe by, and we get this descriptive statistics for, so what this is telling us is for group 0, automatic cars have a mean MPG of 17.15. Basically what we're finding here is that automatic cars are less fuel efficient than standard cars, than stick shift or manual cars. What we're trying to figure out is homogeneity of variance and equal sample sizes. So N for automatic cars is 19. So there are 19 automatic cars in this data set and 13 manual cars. For me, that's close enough, right? 19, 13, there's not much of a difference. So that's good. Now we look at standard deviation. So we can look at variance, and variance has to be a 10 to 1 ratio, no more than that, or standard deviation with about a 3 to 1 ratio, right? So we compare standard deviation for automatic cars and standard deviation for manual cars, and it's about 2 to 1 ratio, right? So that's good. We're under the 3 to 1 ratio. So good. We've met the assumption of equal sample sizes. We've also met the assumption of homogeneity of variance. Equal sample sizes, again, it doesn't have to be exactly equal, but again, much like most stats that we're running, we're taking looks at it and saying, okay, does that seem like it's good enough? The computers, you're just going to assume that everything you're feeding into it is good enough. So you have to visually determine, does this seem like it's good enough? Equal sample sizes met, homogeneity of variance met, independence of observations met. So now we go to the fourth one, and we're looking at normality. So how do we assess normality? Well, we do the same thing. We break out these visual plots by group. So I'm gonna do histogram by group. They look kind of normal, I guess, right? This one looks kind of normal. If we look at the tails, they look maybe a little platycardic, right? We have fat tails. This one looks more normal. The tails don't look as fat. So this might be a more normal distribution. This one might be a more platycardic distribution. Looks normal enough to me. Look at box plots. Let's see, this one's a little off. I think the 50th percentile is about in the middle for both. So that's good. I'm sorry, the 25th through 75th is in the middle of the distribution, so that's good. But here the median is a little bit lower than we would have liked. So for manual transmissions, the median MPG is lower than we would have expected. So that's crazy. It should have been, the median should have been higher. But for me, although this looks off, it's still sort of normal enough to me. Again, you'll hear that a lot. It looks normal enough to proceed. And then finally, we look at the QQ plot. So here we have the normal QQ plot. Looking at this, it seems as though we have a few outliers here, but they don't seem too far from the line. We have an outlier about here. They don't seem too far outside the line. So at least for automatic cars, they look sort of normal. Looking at manual cars, everything seems to be below the line. Right, so the observed value seems to be lower than the expected theoretical value would be. So I don't know, this looks a little less normal. It's sort of supported by what we find here with the box plot. But again, using this information, I'm going to say it looks normal enough, although I probably wouldn't proceed with something like this. There are just probably too few cases to determine if it's truly abnormal or different from normal. So if we had a bunch more cases in here, maybe they would fall closer to that line, right? Or maybe they'd just be as abnormal. But at least with these few cases, even though they're all below the line, there doesn't seem to be a trend where they're all going like waning out from the line, like curving out from the line, right? They seem to bubble in and bubble back and then bubble out, right? And bubble back. So I guess that's normal enough for me. I'm not happy with it, but it's normal enough for me. So we can take this information and then throw it into a t-test formula, right? So we have mean, variance, n of each group. We have the degrees of freedom, n of group 1 plus n of group 2 minus 2, and we can run the t-test formula, right? The t-test formula is down here, t.test, and then in that formula we have MPG as predicted by or as explained by the grouping variable AM, or manual transmission. Right. And then we, based on what we found earlier, that we had equal variances, right? Homogeneity of variances, we can throw in this option that says equal variances is true. So we're going to do that and run this t-test. There's somebody who said something in the chat. Oh, the box plot issue that you might be having, it might be because of the window. Sometimes when you have this window like this, it looks like that. So it's just the size of your window. If you click on zoom and open up a new window, you can actually expand that and it'll show you. No fear, it should look about the same. So yeah, we ran the t-test. So basically all of those steps, 1, 2, 3, 4, 5, were basically just these last three, histogram, box plot, QQ plot, were just confirming normality, right? So in all of those three, we basically found normality. We saw that group 2 or manual transmissions were a little bit less normal, but they were, again, they were normal enough for us. So we met that assumption of normality. This table was the described by function, just listed all the descriptive statistics. That way we can see, have we met equal sample size and have we met homogeneity of variance? So this one call answered one assumption. These three calls, or sorry, this one call answered two assumptions. These three calls confirmed one assumption. So basically we've gone through those assumptions, we met all the assumptions, then we can say, okay, it's good, now we can proceed with the t-test. So we did that. Now we have the t-test. So the t-test says two sample t-test, which is an independent samples t-test. The data are generated from an outcome variable of MPG broken out by transmission type. We see T is equal to negative 4.1, right? Negative 4.1, why is it negative? Let's think back to our Z calculation. Remember we have that Z calculation for our difference of 4, and that Z was 2. but it wasn't just 2, it was positive 2 and negative 2, right? So when we calculate this t-test, it may give you a negative number. It may give you a positive number. And it's giving right now, it's giving us a negative number for that t-value based on which group came first, right? So it's saying the mean for group 2 is higher than group 1. So if you say group 1 of 17 minus group 2 of 24, we're going to have a negative number. If we switch those and said group 1 stays the same, but group 2 is going to be the 0 group, we're going to say 1 is going to be equal to 1. 0 is now 2. Then it's going to switch those groups, and it's going to be a positive t-value. So this is, again, why we do two-tailed tests, right? So it's both positive and negative. So t is equal to plus or minus 4.1. Degrees of freedom, good, 30, right? N of group 1 plus n of group 2 minus 2. So we had 19 plus 13, which is just sample size 32, minus 2 is 30. Our p-value is 0.000285. Is 0.000285, is that less than 0.05 or more than 0.05? Less than, much less than. Sometimes you'll see a number here that's like 2.58 e negative 15, right? It'll look like this, 2.73 e minus 15. You may see that. You have to read this way. It's 2.73. E means times 10, and everything that comes after it is to the whatever power. So here it's times 10 to the negative 15 power. So it's 2.73 times 10 to the negative 15th power. 10 to the negative 15th is basically 10 moving the decimal point over 15 spaces, right? So basically it's 0.000000000000000010, right? If we say 2.73 times that, it's 0.000000000000000273 or something like that. Much less than 0.05, right? So you may encounter something like that. Here we got lucky and we see an actual value listed here, so 0.000285. We know that 0.00285 is less than 0.05. So now we can work our way backwards, right? We use the logic, if t calculated is greater than t critical, that means it's crossed the finish line, it's in the rejection region, we reject the null hypothesis, p is less than 0.05, statistically significant difference. Here, now we're working backwards from p-value. P-value is less than alpha, p is less than 0.05, so now we can work backward. If p is less than 0.05, that means it has to be in the rejection region. That means it has to be rejecting the null hypothesis. That means that our t-value has to be greater than our critical t-value, right? So all of those steps, we can just work backwards from our p-value. Also, we can just look up in a table. We can say, okay, here's our critical, our calculated t-value. Here's our degrees of freedom. We'll use an alpha of 0.05 and we'll figure out what the t critical value is, and we compare that way. So basically, you see this, not even knowing anything else. If you look at the p-value here, it basically says p is less than 0.05. We have a statistically significant difference between these two groups, right? The mean of one group does not equal the mean of the other group in the population. So here we say the output, we see t obtained value is this. So it's plus and minus, degrees of freedom is 30, p-value is that, which is less than our alpha of 0.05. So to interpret this, we report this information. The test used, if you reject or fail to reject, the variables, degrees of freedom, all this stuff. So the way we interpret this is say, using an independent samples t-test, here, I reject the null hypothesis. Why do we reject? Well, because we had p is less than 0.05. That means it's inside the rejection region. If it's less than alpha, it's going to be inside the rejection region. Therefore, we reject the null hypothesis. That we reject the null that there is no difference between the mean MPG of automatic cars and manual transmission cars, comma, in the population. T of 30 degrees of freedom is plus or minus 4.1601, which is what we found here. 30 degrees of freedom is there. And then we say P is less than 0.05. Here, alternatively, I could accept P is equal to 0.000285, right? Either one works, right? 0.000285 is less than 0.05. So as long as you tell me if it's less than or if it's greater than, we'll be in good shape. But that is how you would report this test. Remember, the script window is just going to save everything for future. So if this is just directly copied from the website, the script that I provided, if it's just there, you can save this and just tomorrow you can come back, rerun all of that, and it will run perfectly, right? And then the next day, same thing, right? So you could essentially do this, and then at a later time, you could, rerun the box plot. It'll run. You can export, save image, and you'll have that there. But yes, it'll save this left-hand image. You can Control S. I'm going to go to my desktop. I have my PA606 folder. I'm going to say T test script. And now I have that, and I can use it at a later date. And you can change this however you want to. Like I have it broken down with my comments. There's a line between my comments or above and below my comments. You can remove those if you want. I just figured it might be easier to see what I'm doing and then do it that way. And if you want more examples, on each page with the t-test, with ANOVA, with chi-square, and with correlation, there's the walkthrough that we do together, and there's an example you can do on your own to walk through. So every one of them has an example, which is why I rely heavily on this vignette. So do not sleep on this vignette, please.